So, let me try and indicate to you how these results are proved. Proof 3 is easy. So, proof 1 is very easy. So, let me say 2, right. 2 is saying that let me prove that rho ij is finite. Okay. Rho ij is also strictly positive, which which you can show later. Rho ij is finite, and that can be argued as follows. Okay. You consider your fjj. Okay. Remember what fjj is, right? Fjj of n is the probability that you are in state j at time n for the first time after starting in j, right. So, I am going to consider fjj of m plus n. Okay. So, fjj of m plus n is the probability that at time m plus n, so I started at j and at time m plus n I came to j for the first time. Okay. This I am going to bound in terms of my these probabilities. So, let me actually I need one more bit of notation here. Okay, this probability, this guy here, I am going to call it Lji of n. Okay. This whole probability I am calling it as Lji of n, Lji of n. Okay. It is the probability that I am in state I at time n, given that there has been no return to j. Okay. So, I am going to write, so let me just rewrite it, just Lji of n is equal to probability that xn is equal to I, n less than or equal to tjj, you have not yet come back to j, given x naught equals j. Okay. So, just so that we remember this, and we know that rho ij in terms of this Lji is rho I of j is equal to sum over Lji of n from n is equal to 1 through infinity. Okay. So, now I am going to consider this beast. Okay. So, fjj of m plus n is the probability, if you recall, this is the probability that x m plus n equals j, x m plus n minus 1 not equal to j dot 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 x 1 not equal to j, given x naught equals j. Okay. So, this is the probability that for the first time I got to state j at time m plus n. Okay. Now, I am going to lower bound this fjj of m plus n is greater than or equal to Lji of n, okay, Lji of m times Fij of n. Now, why is this the case? So, what is Lji of m? So, I started state j and I find myself in state I at time m without returning to state j again. I repeat, Lji m is the probability that I find myself in state I at time m, but not having returned to j. Then Fijn is the probability that I for the first time return to j after a further time of n, right. So, the event corresponding to this will certainly lead to the first return to j being at time m plus n. Of course, there are other ways of returning for the first time from j to j. So, this is a greater than or equal to. Okay. So, this I think this you will agree, right. This is always true for any m and n greater than or equal to 1 and any state I consider, right. So, this is great. So, I can write Fi, maybe I should write F. So, Lji of m is So, Lj of m is less than or equal to Fjj of m plus n over Fij of n, okay. And I am dividing because I am taking so n is such that this is positive, okay. This guy is positive, okay, otherwise I cannot be dividing, right. So, if I go back, if I just look at rho ij is equal to sum over m equals 1 to infinity L j I of m, which is less than or equal to sum over m equals 1 to infinity Fjj of m plus n over Fij of n, okay. That is 1 over Fij of n sum over m equals 1 to infinity Fjj of m plus n, okay. Now, this sum is less than or equal to 1 since j is recurrent, right. So, what I have is that rho I of j is less than or equal to 1 over Fij of n, and I have taken Fij, I have taken an n such that Fij of n is strictly positive, right, and that is always possible, that is possible, right, because we are looking at recurrent state inside one communicating class, and this is finite, right. So, rho I j is finite. I will prove later that rho I j is strictly positive, okay. Next, if you want to prove claim 3, which is that expected Tjj is equal to sum over I rho I of j, sum over I belongs to S. So, it is best done using a picture. So, you are looking at, so let us say you are at I these times and you are at k during these times and k and so on, all right. In our earlier notation, if you look at Ri, which counts the number of times you are in state I, right. If you look at sum over Ri, right, what will that be? So, Ri will count that and that, right, Rk will count that and that. So, if you sum over all the states, right, you are looking at the number of times you are somewhere during this this interval, right, which is Tjj, right. So, you have to be somewhere, you have to be in one of the states, right. So, if you sum Ri, you are counting the number of times you are in some state in this interval, this has to be equal to Tjj, correct. So, if you take expectation, so this implies expected Tjj is equal to expected sum over I belongs to S Ri, right. All of this is over, all of this is given that you start at j, right, but I mean I do not have to write this explicitly, right. So, now if you are allowing that, if I take the expectation inside the sum, then you will get sum over I belongs to S. Expected Ri given x naught equals j is nothing but your rho I of j, right. Now, is this are you allowed to take the expectation inside this infinite sum, potentially infinite sum? it requires a justification. In this case, all these terms are non-negative, and the expected Ri we showed is finite out here, right. So, this is justified by the monotone convergence theorem, right. So, we are done proving that expected Tjj is equal to sum over I belongs to S rho I of j. So, basically the argument is simple. Tjj is the sum of all the times, sum of the number of times you are in some state. So, Tjj is equal to sum over Ri, and the pushing the expectation inside the sum is justified by monotone convergence theorem. Okay, that is just a technicality. Logically, it is very easy. The most important thing I want to show you is for I want to show that rho I of j equals sum over k belongs to S rho k of j pki. Alright, this is true for all I. Okay. How do I prove this? So, remember that rho I of j, recall, is nothing but sum over n equals 1 to infinity Lji of n, where I'm just writing that again, right. Lji of n is defined like so. Okay. Now, I am going to condition on, so this is nothing but sum over n equals 1 to infinity. Let me write this out, probability that xn equals I, n less than or equal to Tj j given x not equals j. Okay. Now, I am going to write this out with one more level of conditioning. This is your Lji of n. Okay. Let me call the star. Okay. Now, Lji of n is equal to probability that xn equals I. So, I am going to say xn minus 1 equals k, okay, n less than or equal to Tjj given x naught equals j, and I am going to condition, I am going to basically sum over all the k where k is not equal to j, right. So, what am I doing? I am just using theorem of total probability, right. I am just looking at all the possible values that xn minus 1 can take. Xn minus 1 cannot take the value j, because I am insisting that t less than or equal to Tjj, I have not yet returned to j, right. So, I am just summing over all the other states, not including j, alright. This just turns out to be sum over k naught equals j, probability xn is equal to I given xn minus 1 equals k n less than or equal to Tjj x naught equals j times probability that xn minus 1 equals k n less than or equal to Tjj given x naught equals j. Okay. I have just written out this in terms of theorem of total probability and used conditioning. Now, if you look at this, right, this is the probability that xn equals I given xn minus 1 equals k, x naught equals j, right, and something to do with this topping rule Tjj, right, something to do with this Tjj being bigger than or equal to n, right. So, we can invoke strong Markov property, alright. Because of strong Markov property, place this term will be equal to p Ki. Okay. So, this will be equal to sum over k not equals j pki, and now what is that? That will just turn out to be Ljk of n minus 1. Alright. So, the probability that I find myself in k at time n minus 1. Okay. This you can this involves strong Markov property, and then arguing that you have not returned to j. So, this will just turn out to be equal to Ljk of n minus 1. Okay. So, that is good. So, I am saying that, so what I have shown is that Lji of n is equal to that. So, this I substitute back in star, sub back in star. What do I get? Star is that guy, rho ij equal to sum over n equals 1 to infinity, right. So, I want to take Lji of 1 outside, plus I want to sum from n equals 2 to infinity. Okay. So, this, by the way, if you look at this, right, if you look at this equation, which is very useful, this is valid for n greater than or equal to 2, all right. And what is Lji of 1? Lji of 1 is equal to simply Pji, right. It is the probability that I find myself in state I given that I started in state j, right. Lji 1, I have to go to state I at time 1 given that I started at state j, which is simply Pji. Okay. So, I am taking the term out Lji of 1 plus sum n is equal to 2 to infinity. I am going to sub this back. Okay. Lji of n. So, I am going to write sum over k not equals j pki Ljk of n minus 1. All right. What is Lji of 1? I know this is equal to Pji plus, if you will allow me to interchange the orders of summation because everything is non-negative. So, I will write sum over k not equals j sum over n equals 2 to infinity so, I will just write pki here, pki Ljk of n minus 1, all right. What is this sum? This is nothing but, so I can just, maybe I should just write one more step. I should probably just write never mind this, Pji plus sum over k not equals j pki sum over n equals 1 to infinity Ljk of n. Okay. And this we know to be equal to rho k of j, right. We know that term to be equal to rho k of j, right. So, that's very happy for us. So, this whole thing becomes Pji plus sum over k not equals j pki rho k of j. Okay. But I know one thing, that I know rho jj is equal to 1, right. This is claim 1. So, that I can write this as Pji rho j of j plus sum over k not equals j pki rho k of j. That is because that term is equal to 1, I already know that, right. So, this then you get what you want, right. This just turns out to be sum over all k, sum over all states. So, I have rho ij equals sum over all the states pki rho k of j, right, and that is really that is just saying that. So, this is basically saying that rho of j is equal to rho of j p, right. This is true for all I, right. This equation is true for all I belongs to S. So, I get this balance equation for these rows, all right. So, what have I shown? I have shown all 4 properties, except I think I have to show that remember there is rho I of j I have to show to be strictly positive, right. So, the only remaining claim is rho I of j is strictly positive. Okay. For that we argue as follows. You have rho of j p nth power is equal to rho of j for all n greater than or equal to 1, correct. That is because rho j we showed it to be a stationary, we showed that rho j p is equal to rho. So, rho j p square is equal to rho and so on, right. So, we can use this cleverly. So, what I will do is I will write rho I of j is equal to sum over rho k of j p k I n step transition probability sum over all k, right. I am just writing this in explicit form, all right. So, this p, so there exists n, right, take n such that p j I n is strictly positive, all right. Then I will get rho I of j is greater than or equal to rho j of j p j I n, all right. Now, rho j j is what? Rho j j is simply equal to 1 and p j I of n is strictly positive for some n, right. You take such an n, this is, since this is true for all n, you can take such an n for which this is strictly positive. So, you get it strictly positive, right. So, I have proved everything I wanted to prove. You go back to all these claims. So, this was easy, this I proved in 2 parts, and this was also easy, basically just monotone convergence theorem, and this was my main result, right. So, what is the summary of what I have said so far? I have basically constructed this rho I j as the expected number of visits to I between successive visits to j, right. This has some nice properties. It is a stationary measure, so it is strictly between 0 and infinity, and it solves the equation x p is equal to x, right. So, what we have shown by explicit construction, we have explicitly constructed a solution to x p is equal to x, right, and we have interpreted this solution. And furthermore, if the Markov chain is positive recurrent, you can divide this rho I of j divided by expected of t j j, which is finite for a positive recurrent chain, you can get a stationary distribution. Okay. So, for a positive recurrent DTMC, we have shown that an explicit construction of pi. Okay. So, pi I is simply rho I j divided by expected tjj, right, expected number of visits to state I between visits to j divided by expected recurrence time of state j. Okay. So, this is an explicit construction. I invite you to go over Grimet-Sturzaker's treatment of this. This is essentially it. Then they go on to prove uniqueness up to a multiplicative constant and show that if so xp, essentially Grimet-Sturzaker shows that xp is equal to x has a unique positive solution, unique being unique up to a multiplicative constant, and if sum over all these xi's is infinite, the chain is null recurrent, and if sum over xi is finite, the chain is positive recurrent, and you can construct a stationary distribution among states. All right. So, this I invite you to go through in section 6.4 of Grimet-Sturzaker. I will stop this module here.